Let us pray. Almighty God, who spoke to the prophets that they might make your will and purpose known, inspire the guardians of your truth. Amen.
That's the Reverend Lancaster. On Sundays, he's a priest. From Mondays to Saturdays, he makes fireworks.
You shake my nerves and you rattle my brain. Too much love drives a man insane. You broke my will, but what a thrill. Goodness gracious, great balls of fire.
For these people, fire is a job. They're all experts. Experts in the science of fire and flames.
Firing!
Seems so simple, but there's an awful lot going on in there. Flame. This flame is natural gas burning. And this is where most of it comes from, deep under the North Sea. Understanding how best to burn it has changed our lives. Until the 1920s, this was how most people got hot water.
You get up in the morning at the crack of dawn, you boil one pail of water and the morning's gone.
But during the 1920s, gas-fired boilers became common. For millions, they put running hot water on tap for the first time.
Have you ever tried to wash away egg and bacon with cold water? It's the housewife's nightmare. That's the stuff to give those soup plates, my girl. You'll get through the washing in no time.
Plenty of hot water now.
You need it with boys like this.
And you don't have to have fires in summer to get it. It saves your time.
And softens the bristles. You want it in emergencies.
And you want it quickly.
And you want
it hot.
This flame is very hot, 1,600 degrees Celsius. It's part of an experiment being done by British Gas. One of the scientists is Raj Patel.
In there are two huge flames, which are fed by natural gas and air. And this is pumped through these pipes.
The flame is basically a chemical reaction between the air and the gas. Produces lots of heat and light and also waste gases.
To understand what's really going on in here, you need to get right inside the flame. Fire is a chemical reaction. The flame you see is what comes out of this chemical reaction. Gas is so hot that they're glowing. The chemical reaction happened between fuel, natural gas, and oxygen from the air. But to get the reaction going, it also took heat energy. These are the three things you need for fire: a fuel, oxygen, and heat energy. The chemical reaction produces more heat, energy which is useful. But useful not just to us, it also keeps this reaction going, so long as the fuel and oxygen keep on coming.
One of the jobs I have to do whilst I'm on shift is to take measurements inside the furnace. This involves removing a block from the side of the furnace and poking a probe in there. The probe sucks the sample from the furnace, sends it down a tube to an analyzer, which will tell us exactly what goes on inside the whole furnace chamber. We're trying to reduce the amount of pollution to the environment and also to increase the amount of heat energy that we produce and make the most of this energy.
Making the most of energy means using fuel efficiently. Gas is just one kind of fuel, but there are many others. One particular example is very familiar. Think of a match. A match head is a little package of fuel and oxygen in solid form. Friction with the match box makes heat, and that's what sets off the chemical reaction. This man uses chemical reactions on a much larger scale.
This is where
where I make my bangs.
Dr. Sidney Alford is an explosives expert. He uses the science of chemistry to blow things up.
Firing!
People call for Sidney when they need precise bangs. A lot of his work is cutting up huge pieces of metal, like bits of old ships. Where other techniques fail, he uses explosives. This harmless-looking material is what he uses most of. It's plastic explosive. I was surprised at how little you need for such a powerful chemical reaction, and just how much energy was released.
Here we are. This is very much as to be expected. Look when I turn it over.
Oh, wow.
See, it hasn't perforated the metal. If I'd used much more explosive, it would have done. But it's blown off what we call a spool.
Sidney explained that the power of explosives comes from the speed of their chemical reactions. All the energy is released at once. It was time to open up the portable laboratory to find out what affects the speed of burning.
Sorry.
We started off with the fuel you use on barbecues.
OK, I'm going to take a piece of charcoal, and we've got a flame which is a few hundred degrees. You can't see the flame very well because it's in the open air. You can see it's getting hot now. You may be able to see it's beginning to glow.
A lump of charcoal burns easily in air, but the reaction's quite slow because the vital oxygen can only get to the outside of the lump. But it will burn faster if you get more oxygen to it, say by blowing on it.
Well, we can see how it glows.
But charcoal can be made to burn much faster. Charcoal is the fuel in gunpowder, but even Sidney can't make gunpowder because that needs special equipment. It comes from the factory in little granules. Inside each one, the charcoal has been ground up very finely and then mixed with other chemicals which will provide all the oxygen. That extra oxygen makes quite a difference. In slow motion, you can see just how fast the reaction is. Some quite surprising things will burn if enough oxygen can get to them.
Now, here you have some steel wool.
Steel wool is the stuff people normally use for scrubbing saucepans. It burns quite quickly because oxygen in the air can reach right through it easily. The oxygen is vital. In a different form, exactly the same material, steel, just won't burn at this temperature.
I've got a piece of steel here. It's actually a nail. Now, I'm going to heat this nail, but it's certainly not burning. No sparks. Very unspectacular. I think that you'll agree that we could stand doing this for a month of Sundays, and it's not going to catch fire. Frankly, I am becoming bored with this nail.
But even quite large pieces of steel will burn if you can get enough oxygen to them. It's a process that's used in industry. The flame heats the metal, but on its own, that's not enough to make it burn because there just isn't enough oxygen. Burning only happens when he sends in a jet of pure oxygen through the flame. It's by far the easiest way to cut through steel this thick, but the flame can cut very delicate shapes too. If you can draw it, the machine will cut it for you. Dr. Roger Berrett and Sarah Griffiths are forensic scientists. They work for the police.
Mr. Webb, come in. Right, thank you very much. Hello. Yes, I'm Dr. Roger Barrett from, I think the police officer told you, we're from the Metropolitan Police Forensic Science Laboratory Fire Investigation Unit. This is my colleague Sarah Griffith. Right, so, perhaps you can...
Give us some brief detail.
Yeah.
I sleep upstairs, you see, and I came down the stairs, I put the lights on outside my room, came down, I couldn't see any smoke, I couldn't see anything at all. I was very puzzled, but there was an alarm, one of the smoke alarms, I'd never heard them before.
Mr. Webb didn't know it, but his father was trapped in a smoke-filled room. The problem was, he was over 90 years old.
This is your father's bedroom.
Yeah, this is his room, this is where he sleeps, and unfortunately locks it.
Ah, I see, right.
But I saw the smoke coming out here, so I started to panic. Then I phoned 999.
The emergency services managed to get Mr. Webb's father out, but tragically, he died later in hospital. So what happened? It's Roger and Sarah's job to find out.
OK.
What have we got here, then?
Well, there's fairly extensive smoke logging at high level.
And the main area fire's obviously been here. And in fact, this looks like a piece of pyjama, which might give us a bit of a clue.
Clues are what it's all about. They need scientific evidence to build up a theory about what happened. Quickly, they focus on this. It's an electric heater, and it obviously started the fire.
Which really shows that it's got to have been...
Ah,
that's interesting. What have we got there?
Got a piece of... Yeah, that is lino.
Bit of melted lino.
Yeah, it looks the right shape.
Yeah. So that's got
and there's a line as well.
That's come from there.
If we...
That actually makes quite a lot of sense, doesn't it? Because that's where the main fire damage has been. So clearly that has been
there.
face down.
Like so.
We'll get a nice photograph of that later on with it like that
Yes.
away, so we can see the line. Right. Well, we better just have a look around, make sure we haven't missed anything too obvious. Let's try and sort out where this blanket should be.
Yeah, I think we got it.
What have you got there?
There you go.
Oh, right.
Look, one burnt blanket.
By now, there's enough evidence to suggest that the old man must have knocked over the heater.
Yes, I think that was it.
That looks about right, doesn't it? New paragraph. The actual electric heater has a...
Once they've recorded everything they found, it looks like the case is sewn up.
This is a close-up of the fire, showing the damaged floor level, the flaming damage up the side. Obviously, things have happened very quickly for him to kick this over and collapse. I don't really understand why.
From experience, they reckon it would take 10 minutes for the fire to get going. So why didn't the old man just unplug the heater? To answer that question, they decide to do a reconstruction of the fire in their lab, using a very similar heater standing on lino from the bedroom. Everything's monitored scientifically. The first thing is to check and time everything under normal conditions. After 10 minutes, it's reached its maximum temperature. In this position, the heater is perfectly safe. But what if it were upside down? Then it would bake the lino with its full power, more than enough to start a fire. The real question is, how long will that take? They've predicted it will be at least 10 minutes before anything happens. But there's only one way to find out if they're right. In seconds, the lino's not just hot, it's on fire. It all happened far quicker than they ever expected.
What do you think of that, Roger?
Yeah, that's interesting. Actually, it is amazing how quickly...
Now they understand. In the dark, the old man would have had very little time before he was overcome by smoke. But there's more than a destructive side to fire. Before he became a priest, the Reverend Lancaster was a chemist. He's been making fireworks for years. Now what started as a hobby has become an international business. I went to have a look round the factory.
In fact, it's been discussed at the moment because
So what goes on in here?
he's basically weighing out chemicals which are kept in these blue plastic containers. The chemicals are already powdered when they arrive, and all we have to do is mix them together.
But this is still a very important process. All fireworks work by burning chemicals, but the mix is what makes them burn differently. Fast burns make flashes and bangs. Slow burning mixtures can give different coloured flames. So inside a complicated firework there may be many layers of different mixtures. They take a lot of trouble to make sure that there are no lumps which could change the speed of burning and so ruin the effect.
You must get through a load of chemicals in a year.
We use several tons of chemicals during the course of a year. We probably use about 3 tons of gunpowder, and I suppose we use 1.5 tons of the main chemicals that provide the oxygen, like potassium nitrate, for example.
When that's added, the mixture will burn quite easily, so there's a risk that any heat caused by pressing it into tubes could set off the mixture. So the pressing is done bit by bit. Time to step well back. Once this is over, not much more to add before... And tea. Tea and, of course, crumpets.
So where do you start then when you're making a firework display?
We have to decide what kind of fireworks are really suitable for the place where we're going to set them off. For example, if the people watching the fireworks are going to be perhaps maybe a quarter of a mile away from the fireworks, they would have to be very big and very grand. If perhaps they're watching them from only, say, 100 metres, then we can use smaller fireworks which are quite different.
This is Belgium, and the Lancasters are here to do a big display.
My son, Mark, he's working with me at the moment. We have to go to Knokkelzoot in Belgium in order to do a firework display there. We're going actually for the 2nd time this year. The reason is that they have a competition every year between 5 countries, and so we got the first prize last year. And one of the conditions of getting the first prize is that you have to go the following year and do the firework display on the final night of the prize giving.
Yeah. And then when we get to line 40, we'll have 2 rows, okay? Yeah. Should be no problem. No problem at all. Lots of space. And you think the winds will be coming from over there tonight, yeah?
We're supposed to, but you never know here.
Yeah, hope so.
There's a lot to organise. Setting up an event like this costs thousands of pounds, and they can't afford to let anything go wrong. Mark's got everything all planned out in advance. He's looking forward to seeing some of the fireworks he's made himself, especially for this display. Big display fireworks look quite different.
We push the button, the fire immediately lights these 3 here, it then zips along, 3 seconds later it lights these 3, then after that these 4. All the time the fireworks are getting bigger, the fire comes along here, lights these 4, these go a bit higher still, then the fire shoots along here, 3 seconds later we come up to these which we've made, these go whee! These are really good. And finally the fire zips along to the end, and this one is my baby. I've made this, and with a bit of luck it's going to work, but we're not too sure yet. This is gold to blue, and it goes about 300 feet in the air.
And this is the wire which will set it off. The wire carries an electric current, which heats up an electric match. Then that match lights the fireworks. It means one person can fire the whole display. From here. So how do you get the colours?
The flames that are actually produced by our chemicals are not very highly coloured. And so if we want to make them coloured, then we have to put in chemicals. So we're using strontium salts for red, barium for green, sodium for yellow, and copper salts for blue. But of course there's some colours we haven't got. We haven't got brown, and we haven't got black. Well, perhaps it's black when the fireworks don't work and nothing happens. So basically we have to try and plan the display according to the length of time and the amount of money in the budget, and we try and do it at 2 or 3 levels. Low-level candles, small shells, big shells over the top.
What about the music that you use for the displays?
I'm very fond of Smetana's Moldova River. When you get to the end, you think that that's the end of it and you've put your final fireworks in. But all of a sudden he slows up and then he comes in with another big blaze and it seems to go higher and better. And you can do this in fireworks because you can put moderate amount of fireworks there, then you can put another load in when he does the next bit, then you can put another load on the top of that after that. It's a wonderful way to end a show and it creates excitement.
At last, everything's ready. At the end of the day, what we're watching are chemical reactions. Chemical reactions that produce energy. Energy in the form of light, heat, and sound. A display like this is art, but it needs the understanding of science to make it happen.